Hi, so today we'll be discussing Bayes' rule and a problem that's related to it. So before we discuss Bayes' rule, it's useful to go over some equations from conditional probability. So the first is the definition of conditional probability. So if you have two events, A and B, uh, the probability of A given B is equal to the probability of A and B over the probability of B. So this is the definition of conditional probability. Second equation that is useful to go over is the fact that probability of A and B is equal to the probability of A times probability of B given A. And so this makes sense intuitively because if you want A and B both to occur, one way to do this is to see probability of A occurring, and then given that A occurs, what's the probability that B also occurs? Um, and so let's just keep these two formulas in mind. And so the way to derive Bayes' rule is look at the numerator at the top of the first in the first equation, and we basically use the second equation to substitute in the value probability of A times probability of B given A. So writing this out, we get that, and this is Bayes' rule, that probability of A given B is equal to probability of A times probability of B given A all over the probability of B. And so this is a useful formula for calculating conditional probabilities because oftentimes it's easier to figure out the three probabilities on the right side and then use those three probabilities to compute A given B. And so this is useful in a variety of situations, and we'll see one example below. So let's go ahead and save this equation. And so here below we have a problem that uses Bayes' rule. So let's just go ahead and, um, sorry, paste this. And so now we have Bayes' rule in mind, and let's take a look at this problem. So problem says that we're giving 1,000 coins, and that one of them has heads on both sides, and the other 999 are fair. So we choose a coin and toss it 10 times, and we get heads 10 out of 10 times. So what's the probability that we chose the unfair one? Okay, so let's first identify what the conditional, like how we can use conditional probabilities here. The probability that we want to find is the probability of choosing the unfair one given that we got 10 heads out of 10 flips. So this gives us an idea of what A and B are. So A, the probability that we want to find is the probability that we chose an unfair coin, the unfair coin. I'll just write A equals unfair. And B, the condition that we're assuming is true, is the fact that we got 10 heads, that we got heads for all 10 flips. So I'll just write B is equal to 10 heads. Okay, so now that we define our events A and B, let's try and figure out what the three probabilities on the right side evaluate to. So the probability of A, that's the probability that we got an unfair coin. So as the problem states, there's 1,000 coins and only one of them is unfair. So because we're choosing that randomly, that probability is 1 over 1,000. Okay, let's think about what probability of B given A is. So given that we chose the unfair coin, what's the probability that 10 out of 10 flips we get 10 heads? Well, the unfair coin has heads on both sides, so every flip we're guaranteed to get heads. So we're basically guaranteed to get 10 heads out of 10 flips. So this probability is 1. Okay. Now what about the third probability, the one in the denominator? what's the probability of B? So oftentimes in a Bayes rule problem, this denominator is the trickiest to calculate, um, because in this case, like the probability of getting 10 heads depends on if we chose the unfair coin or not. So we basically have to use what's called the law of total probability to account for these two cases. The law of total probability states that probability of B is equal to probability of A times probability of B given A. Note that this is actually the numerator the numerator in Bayes rule. So then we add probability of A complement times probability of B given A complement. So what this is saying is that if we want to find the probability of B, we can essentially split it into two cases, where in case one, we assume that A occurs, and then we find the probability of B given A. And in case two, we assume that A does not occur, and we find the probability of B given A complement. And so this makes it easier for us to calculate probability of B. So with this in mind, let's try and think about what probability of B is. We've already calculated the first term above. We found the probability of A is equal to 1 over 1,000, and probability of B given A is equal to 1, right? So now let's take a look at the second term. The probability of A complement, well, there's 999 coins. Sorry, this should be a multiplication. So the probability of A complement is 1 minus probability of A, or the probability that we choose one of the 999 fair coins. And then probability of B given A complement. So if you choose a fair coin, what's the probability that we get 10 heads, that we get heads for all 10 flips? This is 1/2 to the 10th power, which is 1 over 2 to the 10, which is equal to 1 over 1024. Okay, so now you can see that we actually have all three probabilities that we need to compute probability of A given B, so now we can just plug them into Bayes rule. So let's just rewrite Bayes rule here. Probability of A given B. So if we look from above, probability of A times probability of B given A, all over probability of B. So it's 1 over 1,000 times 1. All over probability of B, which I'll just go ahead and move that down. Oops. Sorry. Okay. And so this is something we can just plug in directly into the calculator, and it turns out to be approximately 1 over 2. So it's an interesting problem to think about. So it's just probability of getting an probably that we got the unfair coin, given that we saw 10 heads in a row, which seems, I mean, 10 heads in a row is pretty unlikely if we got a fair coin, but also it's also pretty unlikely for us to select the unfair coin in the first place, because so both probabilities are about 1 over 1,000. So it's an interesting problem to think about and apply Bayes rule to. So I hope this helps, and feel free to reach out if you have any other questions.